Stage API 617 barrel compressor. Main idea: inline configurations simplify design but need huge balance pistons, whereas back-to-back arrangements inherently balance forces. Detailed response: inline layouts face impellers one way, generating massive cumulative thrust that requires a leaky balance piston. Back-to-back layouts split impellers into opposing groups, canceling that thrust down to a minimal residual load. Key points: when pressures exceed 10 to 15 megapascals, you must use back-to-back designs to cancel 90% of raw thrust and avoid leakage losses. Traps: selecting cheaper inline arrangements for high pressures is a trap that ignores punishing maintenance costs from piston wear. Key lines: inline optimizes aerodynamics but centralizes thrust. Specify back-to-back for high pressures to protect bearings. Examples: an 8-stage syngas compressor at 18 megapascals uses back-to-back layouts to keep thrust-bearing temperatures safe. Detailed cautions: these require a center stage labyrinth seal. If it degrades, gas recirculation spikes, destroying the axial balance and overloading the bearing. Ultimately, past that critical pressure threshold, managing destructive axial loads completely supersedes the need for simpler aerodynamics.
Question: what fluid dynamic and thermodynamic criteria guide the selection of a hot gas recycle system versus a cooled gas recycle system for compressor startup and surge control? Main idea: cooled gas loops handle continuous anti-surge operations, while hot loops are for short-term warm-ups. Detailed response: as gas passes through a compressor stage, mechanical energy converts into heat. This thermal energy accumulation means an uncooled loop quickly exceeds maximum temperature limits. Key points: cooled systems use downstream heat exchangers to maintain stable suction temperatures. Hot gas paths bypass coolers entirely, strictly limiting them to short startup sequences. Traps: operating a hot gas loop for an extended period during a plant upset ignores rapid heat buildup, leading to severe internal component damage. Key lines: continuous gas recycling requires active cooling. Examples: a cooled loop allows a refinery gas compressor to operate safely and indefinitely at zero process throughput. Detailed cautions: the cooled line must return upstream of the primary mist eliminator pad. This catches condensed liquid droplets before the stream hits the compressor inlet. Thermodynamics dictate the engineering rules. Hot loops are reserved for quick warm-ups, but only cooled loops ensure continuous zero throughput survival.
Trusting a vendor's raw pump curve guarantees catastrophic failure. Here's how engineers audit safety. First, NPSH margins. The main idea: a vendor's pressure curve means the pump is already failing. The detailed answer: pressure drops until performance falls 3%. Cavitation is already destroying the impeller. The key points: your margin ratio must exceed 1.0, even if cooling hydrocarbons make damage less aggressive. The trap is trusting raw data without client margins. Key line: implement positive margins to preserve impellers. For example, demand 4.5 meters of pressure for a 3.5 meter pump. Detailed caution: high energy pumps can still cavitate at triple that margin.